Hey everybody, how's it going? Welcome back if you've been here before, and if you have not, then hi, my name is Greg Hogg, and today we're going to be making actually our 10th project in this playlist. It is going to be in Python and Pandas. We'll do a little bit of numpy and scikit-learn to make various machine learning models on regression. Okay, regression means predicting a continuous value, and the continuous value we're going to be predicting is the price of houses in California. So it's a very well-known data set. There's actually many different versions of this data set. Some are easier, or at least less features or less variables. Others have like many features. We actually have one in the middle here, and it doesn't really matter right now. But anyways, we're going to be making various machine learning models on this, and it doesn't matter if you don't know all of the theory behind all of the machine learning models. It doesn't really matter. We're going to be showing the process of how to try to pick between different models and just how to make these various models in Python. It's very easy. Once you've seen it once or twice before, you'll get really used to it and be able to try new models and test around different things. But for now, it's a beginner project, and don't worry if you don't understand all the math behind everything. It doesn't really matter. Just enjoy the code, and it's going to be really helpful for your own portfolio project. Something that, just picking between various machine learning models, and specifically this one on regression in California housing is pretty well known that people would recognize. So that's both good and bad. You want a model, or you want something that people have seen before, but also you should probably take it, and if you are going to make your own portfolio project, kind of try to turn it into your own more interesting project as well. So I hope you enjoy. The easiest way to let me know if you appreciate this content is to drop a like, and also if you have not been here before, subscribe so that you stay up to date. And yeah, let's just jump right into it. Okay, so to start us off, we have to do a little bit of setup, very little. I'm on Google Colab, so if you don't know what that is, just Google it. It's called COLAB, Colab, and you can spin up this thing called a Jupyter Notebook, which is running in the cloud, and it has all the Python environments set up for you already. Now, we are going to download the dataset from Kaggle, but to get it from Kaggle, that takes a little bit of setup here. So you need to go to Kaggle, and so that's a site right here. And under your account, this is my account, I'm not going to show everything. Basically, under account here, there's going to be a spot to create an API token, and all that is a file that'll download to your computer called kaggle.json. It's just a file, and then you can upload that right here. So I'm going to go ahead and do that off screen, but that's all it is. Create an API token, and then upload that kaggle.json file, and it should show up here. Okay, so now that that's there, we can do a couple things to get this moved into the right spot, and then we can download our data. So what we can do is exclamation mkdir for make directory, and then tilde for home /.kaggle. And for those of you that have done like Ubuntu and Linux stuff, that'll look familiar. Otherwise, it's going to be a little bit new, but it doesn't really matter. cp kaggle.json, and then tilde // kaggle. Okay, kaggle /. Okay, so what we just did here with these is make a folder tilde /.kaggle, and then copied kaggle.json, which we have here, into that folder right there. Okay, and it has to be that exact name of the folder. Then we're going to do chmod, or change modifications, make it so we can make this writable basically. So then this exact same thing. So tilde /.kaggle /kaggle.json, that file we moved in there. And then we're going to download it. So that basically, that was the part that gave us permission to actually download the data set. And now what we're going to do is kaggle datasets download -d Cam Nugent, I guess that's their name, Cam Nugent /California housing prices. And then we should have that as a zip file on our computer, so that we can do, and actually let me just show you that piece before I write the last piece there. Should all be good. And here we have this file here, so I'll just get renamed to get the exact name of it there, and get the name. We can do exclamation unzip that exact name, and then it should inflate, or basically unzip it. We have housing.csv. So now that we have housing.csv here, we can load it in with pandas. So that's just a library for dealing with this type of data. Import pandas as PD, and then I hate how it puts it on my face sometimes. Get out of there. We're going to do, so load it in as a data frame. So we'll do housing, say housing PD, which is for pandas, but it's housing data frame, is equal to pd.read CSV with the name is housing .csv. And then if we do housing pd.head, then there you go. Okay, so I'm going to remove that side there, and we have longitude, latitude, which is location in pairs, housing median age, so the median age of a district. So each of these rows is a data point, which is basically just some district or part of California, and so it has an area to it. It has the overall median age of all the houses in there is 41 years. We have the total number of rooms in that district is 880. Total bedrooms is 129. The population is 322. The households, or number of households we have, is 126. The median income is 8, which I actually don't know what unit that is. Median housing value is 4 million. Is it 4 million? Or no, $452,600. That makes sense. And ocean proximity is the only non-numerical column, which is it shows only near bay here. But we can actually see if we zoom in on that, we'll see housing PD. Just to get this as a column, we can do this sub, give it the name ocean proximity. So I'll just show you that gets the whole column. And so if we wanted to see all the different values it has, we can do .value counts. And so 9,000 of them are 1H ocean. I don't know what that means. Inland, near ocean, near bay, and there's a couple islands. Now, I don't want you to feel like you're stuck in a box here where you have to do exactly what I'm going to say. We could solve pretty much every problem that we want, but the problem that we're going to solve in this one, and what many people have done before, is given features such like features or predictor variables, whatever you want to call it, just kind of things we use to help guess at something. So longitude, latitude, and all these variables, we're going to use those to try and predict the median house value. And so it's called a regression problem. Regression because we're trying to predict a continuous value. This value that we're trying to predict is continuous. So given all these other variables, including this ocean proximity here, and we're actually going to do transformations, and basically just slight adjustments to each of these variables so that this works well. But we're going to use these variables to try and predict this continuous value here. And so we do something called supervised learning for pretty much every setup here, where we have these set of inputs. These are our inputs, including the ocean proximity, and we're trying to predict this output. And we give it many input-output pairs of real data so that we can later, like if we actually to use this model in production, we would just use it to make predictions, and we won't actually have the outputs because the point is to make this predictive model. But we will be able to kind of show that it'll still be good at predicting this output, and so we'll do that. We'll kind of see how well it does based off of if we did have the real answers, then we can see how well it did. But just remember, in the end, we don't actually have the outputs. That's the whole point of making the model. We just need to make sure it works well. And so we're going to do, first, we're just going to shuffle the data set because sometimes, there's reasons that there's actually an order to these things. And for what we're going to do, we don't really want there to be order amongst the rows. We want it to be totally randomized. And so this is very easy in pandas. What we're going to do is just set a new variable, housing PD, we'll just call it shuffled. Shuffled is equal to housing PD, so itself dot sample, where we set the number equal to the length of the housing pandas. So what I just did here is basically said, take a random sample, but include every single thing, because I set the length of the sample to be the length of the data frame. And actually, just to show you what the length of the data frame is, if I did it like this, we can see there's 20,640 rows with 10 columns. Okay, so if I do this, and then also, just so that you and I see exactly the same result, I'm going to do random state is equal to 1, so that's the same every time. And if I ask this thing, housing PD shuffled, we can see there's still the same amount of rows, except here you can clearly see that it kind of randomized things and it shuffled it around. Okay, so that is a good thing. And now what we are going to do is convert this ocean proximity into something that's a little more usable. And this is the concept of categorical variables. I will let you know this isn't the only possible thing you can do, but with only 5, as we saw, 1, 2, 3, 4, 5 different categories, it's okay to do this thing called dummy variables. where basically we just have, there's a 1 on this column if it is that type. So we're going to make this a column, this a column, this a column, and each of those 5 different things a column, and set each of their values to 1 if this row actually is that column, and 0 otherwise. And we'll see if that didn't make sense. You'll see it very shortly, and it will. So we'll do, just to show you at first what it is, pandas.get dummies, where we do housing PD shuffled, and then sub the ocean proximity, and then I'll just show you dot head. Okay, so as we can see here, after it loads in, there we go. So this should match up. So 4712 here, this first row, it is a one, the weird one, 1H 1H ocean, okay? And here, it made this column where it's 1H ocean, and this is 1, and the rest of them are zeros, because it can only be one of them, and each of these rows is whatever one it actually is. So we don't really care about that that column that said which one it was before, because we already have it as dummy variables now. So we're just going to drop this, and that's actually the keyword as well. So housing PD shuffled dot drop ocean proximity, and I have to put this on something called access equals 1, which basically says either rows or columns. And so here, I'm not going to explain it, but basically that's the one we need, is access equals 1. And if I show you the head of that, then this drops it. Now note that this doesn't actually do anything, what I just did here. And this one didn't either. This just made some data frame, but we didn't really do anything with it. And this also made a data frame that we didn't even store in a variable. So housing PD shuffled itself, it's still going to have that column. As we can see here, ocean proximity is still there. So now what I'm going to do is just join everything together. Okay, so I want to join this thing, this dummies thing that I made, with the previous one without that other column. And we do this with something called concat or concatenate. So we want housing PD, and I'm going to call it final, but it's actually not going to be final, so it's kind of a silly name. Whatever. Housing PD final is equal to pd.concat with a list of both of our data frames. So it's going to be, I can just copy it in really. So it's going to be, and it does take the order here, but it doesn't really matter the order too much. But just to keep it pretty much the same, we want this one first, and we do not want just the head. We want everything. So we want to concatenate that with the other one, and that is going to be this. And again, we do not want just head. Okay, so we have that, and like before, we actually need to specify that we want, and is that the right bracket? So it gets kind of confusing here. Yeah, that looks right. And then access equals 1 we need as well. Otherwise it would look kind of weird, and it's trying to stack it. We don't want to stack it. We put it beside each other. So housing PD final is longitude, latitude, blah, 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 up until median housing value, and then it doesn't have that middle column where with the string, it just has these dummy variables as well. Okay, so this is great, and now what I want to do is, it's just going to be easier for us if I put this median house value as the final column, because then I can say our input is going to be everything here, everything but the last column basically, and the last column is just going to be our output, or y. So x is our big matrix of input, and y will be our final variable at the end that we're trying to predict. So now to do this, it's really just a little bit annoying, and there might be easier ways. There probably is, but I'm just going to copy the names, and then I'm going to skip through. I'm not going to show all. Actually, I'll show it to you. Although I highly recommend you skip it, because it's going to be pretty boring and dull, and you'll get the hang of it soon. Basically, we just want to do housing PD final, and as I said, it's not final, is equal to housing PD final sub, and then what we do here is another list where we separate everything by strings. And so I pasted it in here. I copied it from above here, the titles, and I pasted it in. And here, if we highlight stuff, it actually takes a word and it puts it in strings, as long as you put the string button, or like apostrophe or quote. And so we can do that for all of them. Okay, and the ones that are separated by underscores, it's going to put, except they're not all separated by underscores, as we'll see. These ones are not. This is not. Actually, I messed that up. This is right like that. There we go. Near ocean, and that should be right. Okay, so now the only other thing, and it's, I'm sure there's a better way to do this, but I'll just put, I have to put commas at the end of each of them, and I'm gonna just display it. It doesn't really matter how I'm showing it here, but I'm gonna put it 2 on each line, just to make it look good, like that. Almost done, and I'm just gonna stop talking because I'm pretty sure you get the hang of it. And if I test it out with housing PD final, we see that it has everything, okay? And it's in the right order, except it's not, okay? I didn't switch the order, so all we have to do is switch median house value here, put that at the end, so like that. I can just get rid of that, and it looks a little bit silly, but I don't really care. And here, okay, so finally everything with median house value at the end. Sorry, that takes so long, it's just a little bit annoying. Okay, so if we were to carry on our analysis, we would eventually find down the road that there's some rows here. Sorry, I didn't mean to do that. There's rows where some values are basically null values, or null, N-U-L-L, or numpy.not a numbers in here. It basically just means we have missing data, okay? And it's just a way of saying we don't have these numbers. And the easiest way to deal with this, there is more complicated techniques, but it's fine, there's not too many of them. So what we're just gonna do is remove all of the rows that have any value in them, any value in the row that has a null value. And so I keep doing that. So what we're going to do is something very simple. Housing PD final is equal to itself dot drop NA. Okay, drop the null values, and then we can see that the length of housing PD final is now 20,433. So we only lost, what is it, 167, I think, values there. 200, no, that was bad math. 207. I'm rushing it, so I'm not thinking about it. Anyways, only like 200 values or so. Now what we're going to do is split into train, test, and validation sets. And if you know this discussion, then please skip it. Otherwise, it's extremely important. So basically, we're going to be feeding the model in input-output pairs to make it better. Better means trying to decrease some error. We want it to do wanted to get as close to the values as possible. And so to do this, well, it's going to need some actual data that it's training on. But we want to measure how well the model does on data it hasn't seen before, on new predictions, because that's what we want the model to do. So to do this reliably, we split into, for now, forget that I said 3 sets, we split into 2 sets where we have the training, where we do all of the training on it, and then we test the model on this unseen data, and we say, okay, you did pretty well, okay, whatever that may mean. But it turns out we need another set of information, we need another split, because what we're going to do is if we make 10 different models and we're trying to choose the best model, we choose the one that has the lowest test error. But then we're out of data. We've used it all, and so we have no way to say, okay, actually, I think this is how well the model would do. You could, but it's an unreliable estimate, because we've already taken the model that does best on the test error. So we actually need to really make this test thing not seen until the very end. We're going to split this test, or basically the whole thing, into train, test, and validation sets, where we train a model and see how well it does in the validation. Train a model, see how well it does in validation. Then after, we pick the model with the lowest validation error, and then after that, we see how well that model does on the test data. Okay, so we're going to split this into, most of it's going to be for training, and some of it's going to be for validation, some of it's going to be for test. So doing this in Python or pandas is really, really easy. We just want to say, okay, train pandas, train pandas, test pandas, and val pandas. So those are our 3 splits. These are equal to, well, I'll give it, so it's going to be taking it from housing PD final. So we're going to have, we'll give it the first 18,000 rows, okay? And so we do it like that. Actually, no, we don't, sorry, that'll give it the rest. So here, it's basically saying the first up until 18,000. And then we're saving the last 2,433 for test and validation. So we'll make test equal to just 18,000, and then to split it properly, it's going to be about 215. Okay, so it's a pretty even split right there. And if you don't see it, don't worry. Well, I'll show you the lengths very shortly to show you that this is right. And then the last one here, it's going to be, sorry about that, 19,215 until the end. Okay, and if I ask the length of all these things, I can say that length of train pandas, length of test pandas, and length of val pandas are 18,000 of them, then 1215, then 1218. So it's really close. And if I really wanted, sure, I'll put a 16 here so that they're super, okay, there, 17, so that they are extremely easily split. Okay, so there, we just need to convert this now into X and Y matrices, or at least the X matrices are going to be the inputs and the Y's are going to be the outputs, and we'll see this very shortly. Okay, so this part is very easy because we split it up so that all the first columns are the input and the last column is the output. So what we need to do is just split each of our train, test, and val into X and Y's. So I'll do the first one, which is X train and Y train. So the first one's a matrix, rows and columns. The second one is just a vector, and we'll see these are going to be numpy objects. We'll look at them a little bit, but it doesn't really matter too much. So X train and Y train is going to be equal to, so train pandas, so we're taking this from train, and then we're doing 2 numpy. Okay, converting it to a numpy array or matrix, and so this is going to be that, where we specify here now, we want all of the rows, so colon, and then -1, so colon -1 is saying all the way up until but not including the final element. Okay, so this converts it to a numpy array, and then we take all the rows from it, and then just all the columns except the last one. So then that'll be X train, and then Y train is going to be the same thing, except we'll take the colon off the last one because it's saying just the final column. And if we look at this very shortly, we can see X train, actually, yeah, I'll just do that. So that is going to be a matrix here that looks like this, and it has a shape. So we can say X train dot shape is saying, okay, we have 18,000 rows by 13 columns. All right, and it doesn't really matter too much about what this is. It's just clearly a matrix of numbers. All right, and so now we can split this. Actually, I'll show you quickly just Y train as well. So Y train is this. It's just a vector of numbers where we have Y train dot shape. And just to make sure this is clear, we have Y train dot shape as 18,000 things, and X train dot shape. So it has 18,000 rows and 13 columns. And so the input output we're feeding in is each row has 13 values, and it matches up with the first of these, with these Y values. And then we do that 18,000 times. Okay, so now that we have that hopefully clear, we're going to change this into, hopefully you can figure it out for yourself. If not, that's okay. X val and Y val is equal to, we're going to take it from val pandas, we'll convert it to numpy, and we'll do exactly the same thing. Okay, so I'm actually going to copy these things here, and feel free to skip this forward if you know what I'm going to do. Otherwise, enjoy, and that's totally fine. I'm just going to be changing this to val, and then the last one is going to be exactly the same, except this will be converting it to test. So X test, and that's not even close to test. X test, Y test, and then test pandas, and then as well test pandas. Okay, so then if we ask here at the bottom, X train dot shape, Y train dot shape, we saw those already, X val dot shape, Y val dot shape, X test dot shape, and Y test dot shape. These should all make sense. So we have input matrix testing with 18,000 rows, 13 columns, but we're testing it against 18,000 real outputs. Then we have 1218, basically 1218 rows with 13 columns as our input for validation, testing that against 1218 actual values for our output. and then finally 12, 17, and 13, and 12, 17. So now that we have this set up so that it could be fed into many machine learning models, we now need to do something called scaling or transforming the data. And so we're going to do this with something called from sklearn dot pre-processing. So that's another term for it. Another term for transforming is pre-processing. So basically pre is in before training. We're going to process the data, and we need to basically just do something to all the columns. And the main issue is that we don't like how they're on a different scale. That meaning basically the range of values is a lot different. Here median income is only between 1 and 8 so far from what we've seen. But so total rooms, for example, goes all the way to 2,300. So if without transforming it, a lot of the machine learning algorithms are going to think, oh wow, this is 2,800. That's such a bigger deal than this changing from 2 to 3, because this went from 2,200 to 2,800. It gained 700, but really it's not that the actual value is changing. Yes, the actual value is changing a lot, but it's more so very dependent on the scale. And so even though this is only gaining by 1, it's about this maybe the same impact as this gaining by 700. So we have to make these get rid of that issue. And the easiest way to do it, there's probably more formal ways. This is still definitely something that is used, except there might be better ways to do this exactly. We're going to be using just something called the standard scaler, okay? And we'll see what this does. We'll just investigate one column later. Basically, it's going to standardize the data, which is something called, it's going to make it into a normal distribution centered around 0, essentially, each of the values. And so what it does is it basically calculates the mean value for all of these. So just ignore all the other columns for now. It's going to do it for all the columns, but it's going to take a column and it's going to find the average value. And then it's going to make the new, for each of these values, it's going to make it what it was, subtracted by the mean value, divided by the standard deviation. So it also calculated the standard deviation, or the square root of the variance. It's just a measure of spread. And that'll transform it so that basically all of them, every single column, every single value in every single column, they're on the same scale pretty much. We do that for everything except the categorical variables, and we have no need to do this for the output as well. It's only going to be for the input. Okay, and the most important piece is that when we define this this transformation, remember all it is in the end is just adding, subtracting, and dividing by value. It's just a little bit of a function, and so we're doing the exact same function, whether that is for training data, testing data, or validation data. We have to do, I mean, the exact same thing as the exact same numbers. So subtract by 7 and divide by 12. We're going to do that. We'll define that for this column, we'll define that for this column, and whether we're doing it for train, test, and val, it is the exact same thing. We're not going to go and calculate the validation's standard deviation and mean, or the test standard deviation and mean. We won't be doing any of that. It's just figuring it out for the train. That figures out our transformation function, and then we'll do it. So if a lot of that didn't make sense, don't worry too much. I wanted to include that explanation. But let's just go ahead and do it. So what we're going to do is from sklearn.preprocessing import standard scaler. We're also going to need something quick from numpy, import numpy as np. We won't use it very much. So we're going to first fit the scaler, which scaler, again, transformer or preprocessor, it just means it's scaling the data. So scaler is equal to standard scaler dot fit with xtrain. And now what do we actually want to change? So we don't want to change these values here. So it turns out that it is, if we count them, it's going to be starting at 0, 0, 1, 2, 3, 4, 5, 6, 7. And it's usually off by 1 in the high direction. So actually we'd say 8. So we'd say 0 to 8, or just up to 8, which actually only includes up to 7. So that fits the scaler. It figures out the functions that we want to apply to each of these values here. It figures out the standard deviation and the mean for longitude. It does that for latitude. It does that for everything else. So it figures out how to transform a matrix of input, given one of these matrices, how to turn it into these scaled values. So after we've done that, we're going to just make our own function called preprocessor. Define preprocessor, and that's just going to take an arbitrary matrix X, and it'll set A equal to just a copy of X, and then we're going to set A sub, so basically all the rows, and then up until the eighth, or up the first 7 columns, basically, we're going to set that equal to that specific scalar, and notice that it's this scalar, so I fit this based off the training data, so it's the exact same function every time, is equal to scalar dot transform with X, and then all the rows, and then up until the first 7 columns, basically. So we change those values. We don't want to do anything to these categorical variables or dummy variables here, and we just want to return A. Okay, so then if we do this just for one of them for now, that's an arithmetic error, definitely not what I wrote, return A, and then what I can do is set for now just xtrain is equal to, well, I'll just say xtrain preprocessed because I don't want to actually change it quite yet. Xtrain preprocessed is equal to the preprocessor of xtrain. And if I see what this does, xtrain preprocessed, that says operands cannot be broadcast, so clearly I have an error here. Sorry, that should be an A, not an X. That's my bad. Okay, sorry about that. I actually missed something here. This should be all the rows there, and then the first 7 columns. And then I just need to make sure that this runs. I'll do the previous one, and then this. So here, xtrain preprocessed is this. Now, if I just look at, say, the first column, or maybe the second column. Actually, you know what? We can just look at everything. So if I make a PD dot data frame out of just xtrain preprocessed, it turns this thing into a data frame where the columns are just numbers, but that doesn't really matter. And so here, if I ask this thing dot hist, that makes a histogram of each of the columns. And what we'll see here is it tries, it doesn't actually effectively do it. And for here, these ones, these are always going to be just zeros or ones here, but these, it kind of tries to shape it around 0. And if I really pin just on one of these things, because it doesn't really look great, so pd.dataframe of this, and then if I do sub, say, just the first one, say sub 0, I think it'll, okay, here 0, it actually has to be without strings, so this sub 0, we can see it around 0. It basically has this curve here. So it's between -3 and 3 or so, and it's focused around 0. And it's going to be like that for pretty much all of them. It won't look exactly the same, but it's still around 0. And so they're on the same type of scale. And again, this isn't necessarily the absolute best thing that you could do for every single column. Just note that this is a simple pre-processing technique that's easy to do. And so we're going to stick with that. Now, I will leave this part in the notebook, although this is just for demonstration, and I'll just actually put that as .head instead. Okay, so hopefully you have a feel for what that did, and either way, we're going to get moving. So since we scaled all of the data, and we set up our preprocessor so that we can scale either the validation data or the testing data, whatever it may be. So before we start making models, it's really easy if we just do xtrain preprocessed is that, but then we also, actually we'll just make it xtrain is going to be this, and if we do it for the validation and the test, we will have xtrain, xval, and xtest is equal to, I think I copied that, preprocessor, where this is xval, and this is xtest. Okay, and again, I'll just run this previous again to make sure it's right. Get that in, and here. So we should see again, if we ask these things, xtrain.shape, xval.shape, and xtest.shape, they are all exactly as they used to be, and now we can start making some models. Okay, for all of our models that we're going to do, we're going to compare them using this metric called the mean squared error, or actually the square root of that, just to make it smaller, is going to be basically the mean squared error. It's what it says. It's the average, mean means average, squared, so multiplied by itself, error. And so the error is simply going to be y hat, and I'm just going to write out the function for you in pseudocode. Basically, it's going to be, so the error part is y hat minus y, where y is the real value, and just for one data point here. So y is the real value, and y hat is our predicted value. So you can actually write here y hat of x, where x is a vector, where basically you feed in the prediction information. That's this set of variables here it's using to predict. We make our prediction, and then we take away y, which is our error. And then if we do that for over all of the different values, we get the sum of all of these things, and we could say this is basically y hat I, or y hat I of xi minus yi. It's just saying you sum up over all of them, and then we divide by n. That's how we get an average. So then, actually, that's not quite it, because it's the mean squared error, so it's the sum of this error squared. And so might not look quite right, but basically you sum over all of the errors, you square each of those errors, so we have an error squared, error squared, error squared. We sum over all of those, and then we divide by n to get an average. Okay, so it turns out that this is very common for measuring regression problems. It's just going to be a positive continuous value, where the bigger that value is bad because it's an error, and the closer it is to 0, 0 is the minimum, that's the dream basically, the better. Okay, so we can get this from sklearn, scikit-learn.metrics. We're going to import the mean squared error as MSE. We'll just call it MSE. No, why didn't it let me do that? As MSE. And then the first model that we're going to do is just something called linear regression. Okay, it's literally just drawing a line through data. And it's probably not going to be very good, but it might. From sklearn.linear model, import linear regression. So we can make a linear model with lm is equal to, we can do linear regression, bracket, bracket, make one of those, dot fit, and we give it the training data. So x train and y train, we're saying, hey, try to draw a line through with the inputs and through the outputs. Okay, just drawing a line. And so this probably won't do very well. We can get the MSE, where we compare it with the predictions, and we'll do lm.predict with x train and y train. Okay, so that gets the error on the training set, and that's some massive value which we don't like. So that is it by itself, the mean squared error. We can get the square root of this, where if we say square is equal to false, and I don't really like how they set that up, but basically it's just the square root of what we talked about earlier. And so that is now 68,593. Okay, it is technically interpretable, but all we really care about for now is comparing this amongst models and seeing how good we can do. Now, this is the training error. We can also measure the error on the validation set. Remember, we don't want to do it on the test set yet. We're going to purposely hold out that test set until the very end to check after we've created a model, or after we've chosen the best model out of many, then we would use the test. But for now, we can make this xval. So compare the predictions with xval and the actuals, yval. So we have, this is the training error, and this is the validation error. The validation error is unsurprisingly higher than it is the training, because the model actually learned how to fit this input to that output. We want it to so-called generalize, and hopefully get not that much a worse an error on this than we did. We don't want these errors to be too much different. If this error is way, way, way higher than it is for the training, and it's hard to tell right now, but it doesn't look too bad given the size of the numbers. If this was way bigger, we'd have an issue called overfitting, which basically means our model tried too hard to fit this particular data, and it's not able to generalize to new results. So anyways, there's our first linear model, and it's tough to say without comparing it with other things, but it's probably not going to do very well. Something else that is actually always nice to try is something called k-nearest neighbors, which is really just an algorithm which compares each of the, we say nearest as in a Euclidean distance. I actually don't really want to explain it too much. I would check it out by yourself if you're interested. But it's basically just saying, given this input, memorizing what's in the training set of information, find the things that are closest to you, and then just check what their output is, and then average them. So if we say maybe got the nearest 5 neighbors, set k equal to 5, so it would be 5 nearest neighbors, then for each point it would find its 5 nearest neighbors, check what their outputs were, and then it would average those values to get the output. So we can do from sklearn dot neighbors. Want to import a k-neighbors regressor. Okay, it's a regressor because we are trying to predict a continuous value. We're not classifying in this one, so we're doing knn is equal to k-neighbors regressor. We have a what's called a hyperparameter here. We can adjust this value, which is the number of neighbors. We're setting k here. I don't know why they didn't just call it k. They called it number of neighbors is equal to, maybe we'll just try whatever its nearest neighbor was. We'll just take its value and then dot fit x train with y train. And now let's just copy this, but we're going to change it. No, sorry, keep that. And then we're going to change lm to knn. That's the only change we have to do here, I believe, ever in our whole thing. It's pretty awesome. So here, that I must have messed something up. knn.predict on x train, even though. So it says it got 0, which, right, this actually makes sense because the error should be 0. If I'm not going to explain it, but with number of neighbors equal to 1, that actually will happen. And so now here, if I set neighbors equal to 2, notice we have a much lower training error than we got over here, but we don't care how small the training error is. We care about the validation error. So we do see what's called overfitting. We overfit really badly, and it turns out that if already we got a smaller value here, but it turns out if we increase the value here, then we're actually going to reduce the overfitting problem. And so these are going to get closer together. We get 3, they're a little closer together. 4, they're also a little closer together. Let's try something like 7. And here, they're a lot more closer together. We have 62,000 here. Let me just try 10 for fun. And there, 62,000. Let's actually keep that. I'm relatively happy with k-neighbors is equal to 10 there. It's already much better. We could play around with that more if we wanted to. So done with k-nearest neighbors, we're now going to do something called random forest. You may have heard of it. And again, don't worry if you don't understand all the math. I'm definitely not going to explain what this is doing here. Basically, we're going to be doing something called ensemble, and that's why it's from sklearn.ensemble. We'll import the random forest regressor, not classifier. And so basically it just makes a bunch of different decision trees, and we can actually specify the number of trees here, although I'm not going to adjust that. We'll just make it whatever the default is. And it basically just combines a bunch of these trees' results to try and make an overall prediction as to what the value is. So here we'll just call it RFR is equal to random forest regressor. And we're just going to adjust something so-called the max depth of the trees. So the trees have some sort of depth, and we can set it equal to maybe 2, okay? And then we'll fit it with X train and Y train as normal. And then we can copy the exact above, except instead of using KNN, we want to use RFR. We'll do that and that. Here's our errors, and we get 80,000 and 80,000. Okay, so it did not overfit at all, but it didn't do very well. So it turns out if I increase the depth of the trees, you might think intuitively this might increase the complexity of the model. Maybe it'll do a little bit better. So max depth is equal to 4. And now we have 70 and 72, so we overfit a little bit because the difference is apparent, but we still lowered it a lot. We'll try equal to 6 here. And yeah, we could absolutely change the number of trees here. I just want to choose one value to adjust. So we got 65, 61, and 65. Not bad. Let's try maybe 8. One more here, and every time it probably is taking longer and longer the number as I increase the max depth here. It makes it a more complicated model, but there we got down to 53 and 57, so a little bit of an overfitting problem as well, but we got the validation error lower as well. And let's just stick with probably 10 here is going to be fine. If it's that much worse, then we can go back to 8. It doesn't really matter. You kind of toy around with these things and pick whatever you want to pick. There. So I'm pretty happy with 43 and 53. It is great. We already got an improvement. We started with 71 with the linear model. Then we got 62 with the k nearest neighbors with 10. And now with random forest, we got it down to 53. Okay, so this is great. And now we're going to do something called a gradient boosting model. It's even more intensive most of the time. From sklearn.ensemble, so it's still an ensemble model, we're going to import a gradient boosting regressor, not classifier. And it's going to look exactly the same. So I'm going to copy this pretty much all together, except I'll change this to gradient boosting regressor. This part is going to be gradient boosting regressor, and GBR down here, GBR down here. Now, again, there's some parameters that we can tune here. I'm not going to talk about all of them, but we're going to change this thing called n estimators. We'll set this equal to say 1 for now. And we can see we have a lot of error. It made it very simply. If we make it say 10, then we already decrease it significantly. If we bump it up to say 30, then, as you can see, it's already taking a little bit longer to produce, but here it's clearly going down. Let's jump it up to, say, 60, and it goes down again. We can see we have a little bit of an overfitting problem, not too bad. If we change this to, say, 100, what's going to happen? It's going to take a little bit longer to run, but GBR is going to show there. Okay, almost as good now. And let's set this equal to maybe no, not 010, that doesn't make sense, 170. I don't know. It's going to get more and more complicated. We might start to see an overfitting problem, not sure. But there, yeah, so a little bit overfitting. We can see about the same error here. Maybe if I try something just a little more complicated, maybe a whole 250 estimators. I know I'm not explaining what the gradient boosting model does, but you can see as we tune this, we get a little bit more of an overfitting issue, but also it seems to do a little bit better. And there, we actually got a better result here, okay? And you could probably tune that as well to get a lower validation error, except we're pretty happy with that because it went down again. Now, that is it for what we're going to do with the scikit-learn estimators. So we did linear regression, k-nearest neighbors, random forest, gradient boosting. That's pretty standard. And now we are going to make 3 different neural networks. Feel free to use PyTorch if you prefer, but we're going to be using TensorFlow and Keras. It's very, very easy. So we're going to start with just a bunch of imports, which is from TensorFlow, TensorFlow.keras.models. We're going to import the sequential model to make a neural network. We're going to do from TensorFlow.keras, import star. We'll do from TensorFlow.callbacks, TensorFlow.keras.callbacks. We're going to import model checkpoint. Okay, I'll explain these things after. From TensorFlow, this one you'll understand. From TensorFlow.keras.metrics, want to import the root mean squared error. And finally, we're going to make an optimizer, and I'll explain what that is, from TensorFlow.keras.optimizers, import atom. Okay, so now what we made here, so sequential, basically we're going to make a neural network out of many layers in order. And so sequential, it's like an in order set of layers. Here we have layers, we imported all of them. So we just imported a bunch of names that I have memorized and I know what we need, but I'll show you what we need. Model checkpoint is something that basically, as the model trains, it trains in these things called epochs. So an epoch is one run through the training set. So it goes through the training set, makes some updates, it goes through the training set, and it may actually make multiple updates throughout an epoch. But an epoch is basically when you can say that it's just gone through the training set, and we can do whatever we want after that in between runs. So a model checkpoint, this is going to be for saving the model. We'll just save it to some folders over here. It's very easy to save and load models. And we can use model checkpoint to only save the best model. And the best is going to be the one that has the lowest validation loss, as we'll see. We also have root mean squared error. That'll be us to report and compare with these numbers above. And the optimizer atom we will see lots of soon. So we're going to make what's called first just like a, well, I'm calling it this. It's a shallow neural network, or actually it's not technically shallow, but we'll do a simple neural network. It's very, very easy to do. It's sequential. Okay, bracket, bracket, and then we just start adding layers. So we can do simple nn dot add with an input layer of, okay, so we're going to specify a shape. And so this is 13 things as above. And generally we put a comma there to make it happy. Okay, if we remind ourselves here, yes, we have 0 to 12, which is, this is our input. This is our 13 things that we need to input. So now we need simple neural network dot add. We're going to add two what's called ReLU activations. And I'm not going to explain too much about the deep learning stuff, but essentially we transformed it from 13 inputs to then two inputs. And then after that, we know we need to convert it into just one value because we're doing a regression problem. It's just predicting a continuous variable. So we'll do simple nn dot add a dense one, which is linear, and linear means like a continuous value. So now we're ready to train this first model. We'll specify the optimizer, and I'll explain this again shortly, is Atom with a learning rate equal to starting it. 0.1 seemed to work for me earlier, but I'm going to purposely play around with these things and show you exactly what the impact that this does. So if I don't even specify a learning rate by default, it's going to pick, I believe, 0.001. And we can make a CP equal to model checkpoint with, sorry, that's BASD. Models, we'll just choose a folder here. It doesn't really matter. That doesn't have to exist yet. So models / simple nn, we're going to make this, so that we don't even have a models folder yet. It'll make that models / simple nn. And then we're going to save best only is equal to true. Okay, so only save the model that has the lowest validation error. That's the one we care about. So we'll do simple nn dot compile the model, it's called, and we set the optimizer equal to our optimizer from earlier. This is just how it decreases the error, decreases that mean squared error function. And we specify here the loss, or the error. We want to minimize the MSE, which stands for the mean squared error. We will actually report and view the metrics equal to the root mean squared error, bracket, bracket, like that. But that's just for viewing it. It's trying to minimize the MSE, but don't worry if we care about the root mean squared error, it's still minimizing this by minimizing that. Okay. So now we can fit the model, and we do simple. No, why is it still wrong? Simple. And then dot fit, so train the model with x is equal to x train, and y equal to y train. We can set the validation data, so we can actually view the validation data as it goes along, as we'll see, or the validation errors. So we can do validation data is equal to the tuple of x val, and y val. When we can set the callbacks, so to make sure, this says at the end of every epoch, what do you want to do? We want to call CP this checkpoint we made earlier, which says, do we want to save the best model to this area? I'm not sure. Depends on the validation error. And set the callbacks to be that. And then finally, we need to specify the number of epochs. So I'll say epochs is maybe 100, okay? We'll let that run, and I'll show you what happens. Is here we can see each of these is epochs, and it runs through the data. We see a massive loss, which is that mean squared error. We can view the root mean squared error as well as the loss for both the validation. Sorry, I need to grab it here. The loss for both the validation and the root mean squared error as well. So these are way bigger. To start, this is 237,000. Before, remember, we were getting 47,000 or 52,000. So it needs to go down a lot here. And it looks like it's not even getting better. And that's because the learning rate is just really slow right now. So we need to specify here, hey, make bigger jumps, make bigger optimizations. Let's set the learning rate to be instead maybe 0.1. And now I don't know why that thing at the bottom there showed up. So now what it's doing is making huge adjustments. Okay, so you can see here, it's going down a lot faster. And there might be a trade-off here, technically, and I'll show you as well that before we actually make a model, is if I make this, say, the learning rate equal to 10, well, check this out. It's going to start training, but it'll do it extremely fast, and that seems awesome because it's like, wow, it's training so quickly. Isn't that what we want? But actually, you'll notice it's not even really saving the model anymore. It can't get any better than 68,000. And maybe that's true. Maybe that is the best possible thing that we could get. But it turns out that if you set the learning rate to something in the middle here, something like 0.1, well, yeah, it's going to take a little bit longer to get there, but hopefully it'll actually do better than that. We'll see if it really does. Okay, so I'm going to let that finish up its training. It's almost done, but without looking at that, what we are going to do afterwards is just load the model and then check the accuracies like we did above. So actually we can see here already the value, actually it's about 68,000 like it was before. So maybe that was a good learning rate, I don't know. But so we want to do from TensorFlow.keras.models import load model. Okay, so this allows us to, it's going to save it. Actually, we can see here, it saves the model to this models, and then whatever we called it there, directory, and we can load it like this. So we can do simple nn is equal to the load model of models slash simple nn. Okay, so we load that in. And then we can just do the prediction as above. So actually, what is the, yeah, so here we actually did beat it. Val root mean squared error is down to 67,000. So this is a better learning rate. So now if we take what we have above, the MSE, we can grab this in as MSE is this with simple nn dot predict and simple nn dot predict. And after, I think it's just fixing it up here. So we actually did write to it on the very last epoch, which is interesting. We ended with a root mean squared error on the validation of 67,767. And that is, not as good as the other models. It's only better than the linear regression model. So if we can actually, well, we'll see this in a moment, and I'll let this run. But we can see here already that the difference between these two is not that much. And so they're both not that great. It's actually doing something called underfitting. It's also overfitting kind of a little bit at the same time. But the model could do a lot better. If we increase the complexity of the model, it should be able to get a lower error than this. If we make a more complicated neural network, hopefully we can see both of these go down. So here, it's the same, pretty much the same values here, not exactly the same. And yeah, so those are our errors. And we're ready to make a more complicated neural network. So we're going to go above. I'll just cancel this output for you. And we're going to make something called medium neural network. Okay, so this is going to be something that's kind of just a little bit more complicated, but not crazy complicated. And we will make crazy complicated after this. So I'll change this to medium NN, all of these, and as well as that name right there, and these two. And actually, I can go ahead and copy these this valuation as well. We'll do this after with medium NN is that, loading in medium NN, and that, and that. Okay, so this is now set up, but to actually make a more complicated model, we're going to do something like, say, I don't know, making maybe this equal to 32 ReLUs, and this equal to another hidden layer, what we call it, is maybe 16. So this is a decently complicated neural network. Let's see if that manages to get a lower error, and I'll see you basically after that's done training. Okay, that model is done training, and it got 51,000 on training and 56,000 on testing. So we can see it definitely is overfitting a fair amount. There's a big difference between these two here, but still, we got the validation down to 56,000, and that's a lot better than that 67,000 from the previous neural network. As well as down here, it's just a little bit worse than the random forest type models. And it's, again, better. It's now better than the k-nearest neighbors regressor. Okay, so we'll try in one more model. It's going to be tough to avoid the overfitting part at this point, but we can copy this in and make something which I'm just going to make basically just a large neural network to see if this really does solve the problem. It probably won't. Large NN I'm going to copy this into everything here, as well as the training or the evaluation before. Okay, I think that's everything, and now we can go ahead and just make this crazy complicated. So let's add in some layers here, and so let's try, I don't know, 256 of these values, then 128 of them, then 64, you can see I'm choosing powers of 2, maybe 32, all the way down to 1. So who knows? Maybe this makes it better. It's probably going to run into an overfitting problem, but I'm going to let that run and we'll evaluate it. And I'll see you after that and see how it goes. Okay, that model is done training too, and we got, again, an overfitting issue, but we did get it down to 53,500 compared to, and I'll just delete that, compared to the previous one, which is 56,000, which is pretty much on par with the other one. So this is 53 and 51, but still, so far, we like this gradient boosting model in terms of accuracy best so far. So that's going to be it for choosing our various models, and we're going to say, okay, I guess we're happy, or most happy with the gradient boosting regressor if we're only considering accuracy. Okay, there's also a trade-off between inference time sometimes, which means how quickly does your model actually run in production. That's something to talk about, but for now we're just going to choose the one best on accuracy, and it will be this one. So we'll just say, okay, we choose the gradient boosting classifier model, and we want to see how well it does. We want to see, okay, hey, how good is our actually model? How actually good is our model? We want to tell our boss or whoever we made this for how good we think it's going to perform. And we'd say something like this, or we'd give it the predictions on the test data, comparing it to Y test. And we only need that one, so I'm just going to produce that. And we'll say, hey, we're pretty sure it's about 49,000, which actually seems to be better than it was on the validation, which is, I mean, I guess it doesn't really, there's little correlation there between the two. So I guess it's okay that it's less than that. It is actually, better. And yeah, so there we go. We've picked a final model, the gradient boosting classifier model. We said how well it did at the end. And that is our project. So I hope this was helpful to you. Again, if you got here and you haven't dropped a like, please do that. If you have not subscribed, please do that so that we can get you more of this content all the time. And yeah, I hope you like it, and I'll see you in the next one.